All right, let's work through number 5 now. So number 5 is a question about intertemporal substitution, which is a concept we'll talk about tomorrow in class on Friday. Um, I'll just, so this problem is sort of, it throws a little twist into the classic intertemporal optimization problem. So I'll just walk you through the sort of canonical intertemporal consumption problem, utility maximization problem, and then we'll see how this this additional tax that's added into the cost of consumption, it's not affecting, it won't affect the marginal rate of substitution. That's what this term is right here, right? It's not affecting the marginal rate of substitution for between the two periods, from consumption between the two periods. So it's not going to affect MRS, and it's not going to affect this relationship, the ratio of consumption that we have in the current period versus the future period. But so with that preview established, let's go ahead and work through the problem. So this is problem number 5. Intertemporal. What was it? Optimization or substitution? All right. All right. So even before we get into the this problem that has sort of the tax twist in it, we can just work through the classic problem, which is we're trying to maximize utility, right? We have this utility function that's defined by our present consumption plus our consumption in the future period. I won't be too lazy here. I'll go ahead and make that look nice, which is 1 plus, I can't write now, 1 plus delta. So basically it's like we're discounting this future consumption because we'd rather consume now than later. And so that's what this discount factor delta is capturing. So this is our utility function. And then we have this budget constraint where we're going to get income in this current period and we'll get income in the future period. And we could save some of this present income to, it'll earn an interest rate. So, if we don't consume some of our income now, we can invest it, it'll earn a rate of return, and then we can consume it in the second period, or we could borrow some money and pay this rate, this R rate, and to consume more now. If we just are really impatient, we could borrow and consume more in the present period. All right, so this is our budget constraint here. So it's just how much we consume in the first period plus how much we consume in the second period over 1 plus R. And then obviously that can't exceed our income, which is defined by this equation here. So the consumption is going to be equal to the income. We're just going to assume the constraint is binding. Like you could technically not spend all of your income, but it doesn't make any sense. There's only 2 periods in this world, and then I don't know, we all die or something. So it's like there's no third period for which we'd want to save money. So it's going to be a binding constraint, right? And so we're going to maximize utility with our selection of consumption by our choices of C sub 0 and C sub 1. And so we're going to need a Lagrangian, everyone's favorite mathematical tool. So to set up the Lagrangian, right, we're going to choose C sub 1, or excuse me, C sub 0 and C sub 1 that maximizes our utility. We add this lambda plus our constraint that we're going to rewrite. It's going to look like this, 1 plus R minus these terms over here, C sub 0 minus C sub 1 over 1 plus R. Okay, so this is like the classic optimization, intertemporal optimization problem. We've got to set up, now we need to write out our first order conditions. So we need the partial with respect to C sub 0. Oh, this is getting ugly here, sorry. The partial with respect to lambda. We actually don't really need to write out. I mean, technically we could solve for the shadow price too, but we don't need to in the question, so I'll just take you through the relevant parts of the canonical example. All right, let's solve this. So we would get U prime C sub 0, and then C sub 0 appears here too. Power rule goes away. It's going to be minus lambda equals 0, or we could rewrite it as this. And then for C sub 1, we'll get U prime C sub 1 all over this discount term here, 1 plus the discount rate. And that's going to be subtracted by, here's C sub 1, we take the partial derivative. So we're going to get 1 over 1 plus r, or we could rewrite it as U prime of C sub 1 is equal to, oh, we need to set it equal to 0. Right, we can move this term to the other side, multiply by 1 plus delta by both sides, so we get 1 plus delta over 1 plus r lambda. And then, so the marginal rate of substitution, right, this marginal rate of substitution tells us how we're willing to trade between the two goods, and we want the marginal utility of our consumption to be equal to we want the ratio of the marginal utility of the consumption to be equal to the marginal cost of the consumption in those two periods. So that's what this term is giving us. That's sort of what marginal rate of substitution really means. How are we willing to trade between these two? And we want them to sort of have the same, sort of like, when we talked about producer theory, like we want to consume, or we want to use as much labor and capital. We want to use them in ratios that reflect their costs too, right? And if one is more effective per cost, then obviously we're not at an optimal point. So hopefully that example is helpful to illustrate what this concept is and what the equilibrium is going to look like. So we can just take these two, right? The marginal rate of substitution is going to be this term right here. We can just take these two first order conditions and divide them by each other. Excuse me. Lambdas are going to go away. This is on the bottom, so this denominator here, so it's going to be flipped. 1 plus r over 1 plus delta. So this would be the marginal rate of substitution in equilibrium in the in sort of the canonical case where we don't have this tax term put in in the mix of the intertemporal problem. So let's clear this and let's add in, right? Okay, so even before we do the math here, intertemporal substitution. So we have a different problem here, right? We have a budget constraint that looks like this, 1 plus t. So we have to pay a tax on whatever we consume, plus 1 plus t times c sub 1 all over 1 plus delta, our discount factor. And the budget constraint, it's unchanged, right? Let me read this real quick. How does the consumption change? Yeah, okay. So then our budget constraint is going to be, I've written it here. It's going to be binding, so it'll still be equal to our income in the two periods, and then the income in the second period divided by the 1 plus the rate of return. How does this consumption tax change U prime, this marginal rate of substitution between the two periods? Well, because the tax, so if we look at the tax, where is it? Right here. In the current period, we pay the tax. And in period one, excuse me, current period, and then period one, the next period, we pay the tax, and it's discounted by the rate of return too. So this is not, these are affecting the price of current consumption and future consumption in the exact same rates. So even without doing any math, we could just reason that it's not going to affect the marginal rate of substitution because it's not really affecting the ratio of prices. And so it's not going to affect the ratio of our consumption of C sub 0 and C sub 1. I mean, the tax, it's like effectively reducing our income. So we'll consume less of C sub 0 and C sub 1, but we'll consume less in the exact same ratios we'll consume less, but we'll consume them in the same ratios as we do in the current mix. So I could walk you through this same problem again, right? We still have the same utility function, which is U of C plus U of 0, C1 all over 1 plus the discount rate. It's going to be the exact same steps I showed you before, except there's the 1 plus t term, and you can show mathematically. I'm not going to go through it because it's just more math, and that's really not the purpose of why I'm making these videos. So you can rewind it and look through the math again, but it's not going to affect u prime of c over u prime of c1. Like it's going to be the exact same ratio. We can just pull 1 plus t out of it. So it's everything's it's going to be unchanged. Unchanged MRS, unchanged C sub 0 over C sub 1, right? These ratios are still going to be the exact same, but C sub 0 is going to be lower. We're going to consume less in the current period and less in the future period. And if you wanted to do all that math because the intuition is not apparent to you when you're reading the question, well, just go through that optimization problem. But now it's going to be a little bit more complicated because you have these 1 plus t terms that have been thrown in there. All right.